Now let's do an example with triple integrals of the Jacobian. So let T be a transformation that maps the region S in UVW space into the region R with XYZ space. So the Jacobian is roughly the same thing, it's just triple integral, so you have to define the determinant of a 3x3 matrix. So it's a little lengthier process, but it's still technically doable when it comes to this change of variables. Okay? Where the integral is the same thing, is the function in terms of all three change of variables times the Jacobian, and evaluate all three itself. Okay? So let's try an easier example with triple integrals so you can see how this would work. All right, so find the the region of, or find the volume, because we're doing the triple integral, where E is the solid enclosed by the ellipse, x squared over a squared plus y squared over b squared plus, this is supposed to be z squared over c squared equals 1, and use the transformations. So they give us the transformations, which is nice because this is going to be a little pain to deal with. Okay, so first off, let's just figure out what's going on. So if we just quickly draw this. No, I'm not going to draw the ellipse itself. I'm going to draw its transformation. So if I plug in a for x, y, z into here, notice the a's will cancel, the b's will cancel, and the c's will cancel once you square it. So we just get u squared plus v squared plus w squared equals 1. So if I do this transformation, we'll say this is w, u, and v. This is this tetrahedron here now. Or really is it? Because if I do this, that's interesting. Looks like a sphere. So that'll be a little hint for later on. But for now, we want to convert this stuff. So what we want to do is now, okay, given this value, how do we find our bounds after we do this change of integration, right? Now the good thing is when you graph this, you could tell, right, just using the x-intercepts and the y-intercepts, or in this case the u, v, w intercepts. So if you set 2 of them equal to 0, you go to 1 to 1 to 1. So this is going to be the triple integral of all the variables just going from 0 to 1. Now the question is, what am I actually integrating? Because it just says dv. Okay? And that's an interesting aspect because we're trying to find the volume of this solid generated. So if I go to my transformation here, it's actually not a trapezoidal, it's actually a circle. Right? This is a sphere. And the volume of a sphere is equal to 3/4 pi r cubed, where r is radius. In this case is just 1. So what we're doing is finding the volume of a sphere. Or we're doing a triple integral of the volume of the sphere. And r squared is, r to the third is just 1, so it's just that du, dv, dw. Okay. So the only thing we notice, right, this is a complete constant. Next thing we got to figure out is the Jacobian. Multiply, and then we'll just do this integration 3 different times. Okay. Well, let's see when we get this Jacobian. So the Jacobian is going to be a 3/3. And this with respect to, so take the derivative with respect to u, just gives me a. Respect to v is 0, and respect to w is 0. Now to y, same process. Respect to u, respect to v, respect to w. Respect to u, v, w. Right, we're just doing partial derivatives. And remember, when it comes to the determinant of a 3/3, you do this row times this box and so forth, but you notice there's zeros here, so everything besides the first one ends up being zeros. So this ends up being the determinant times the a value of this part right here. which just gives you this times this minus 0, so a, b, c. So it's this whole integral times a, b, c on the outside. Which is not great. This is a constant, so that's just 3 to 4/3 pi u. Evaluate at 0 and 1, which just gives you itself back. Okay, well, we do it 2 more times because that goes the exact same process. And then I'll just put a, b, c on the outside, dv, and notice you just get the same thing. So this is just the last integral. Again, it's 0 to 1, so they just get this. And that's our answer. Now the interesting part is, this is why this is such a cool question, is because this is the exact volume of an ellipse. That's the cool thing. So this simple transformation from that goes to u, v, and w here, which end up being a sphere, we use this volume of a sphere integrated over the boundaries from 0 to 1 of each individual case, and we get the general equation for a volume of an ellipse. So this is kind of like the proof of why the ellipse formula looks like this. So where a, b, and c are these constant values down here. So it's a very interesting question. If you guys are ever wondering how a lot of these questions come into play, non-geometrically, right? Using the algebraic approach, in this case, the multivariable approach to solve for the volume of an ellipse using the equation of a sphere. Okay, let's try one more example down here. So we'll go back to 2 dimensions. So find the double integral of this region over the region where the region R is enclosed by the lines y minus x equals 0, x minus y equals 2, x plus y equals 0, and finally x plus y equals 3. So a lot of things happening here, right? So I always like everything in terms of y equals. So I'm just going to break a couple things. So if we rewrite all of this, so we'll have y equals x for the first one. So x minus 2. Here, y equals negative x. And over here, so be y equals 3 minus x. Okay. So let's graph this transformation and see what's going on. Or not the transformation, the actual curve. So going from xy okay, so y equals x is just a straight line from here to here going in this direction. Y equals x minus 2 starts at 2 and up 1 over 1. So kind of like this. Okay. All right, y equals negative x just goes the opposite direction. So it goes down here instead. So it looks like this region here. And then finally, so it starts at 3. The x-intercept is down here. So kind of like that. So the region we're looking for is right here. So this is a region R, and we're taking the integral of this over this region, okay, which kind of is a pain to deal with from there, right? Okay. So when we do this change of balance, because this is going to be a pain to try to integrate normally, we get to choose what x and y, let's say, for example, u and v are going to be. And I'm just going to rewrite this part right here, because that's a difference of squares. Like that. And in fact, why don't we just let those be u and v? So we'll let u equal this part, and v equal this part. So we have u is going to equal to x minus y, and v is going to equal to x plus y. So notice right off the bat now this converts us to v when we do our integration. Okay. All right, so now we want to figure out bounds of integration, what's going on here, right? Okay. Now for that, we're going to go here. So we're going to go from here to there. Okay, let's see what we get here. Now, this one's going to be a little different than the last one because we're not going to actually use the points themselves. We're going to use the equations themselves, because if you noticed, that's exactly what these are, right? X minus y equals 0, so therefore u becomes 0 at this point. X minus y equals 2, so u goes to 2. V, x plus y equals 0, so v equals 0 on this point. And over here, x plus y equals 3, so v equals 3. So this is the rectangle looking like this. Isn't it interesting? So this gives us our bounds already. So we'll do u first. So this goes from 0 to 3 and 0 to 2. Our function, so x plus y was v, e to the u times v, times our Jacobian we'll get right now, du dv. Okay. Now for our Jacobian, we have to do the same thing. We have to solve for x and y. We did this in the last example, right? So this ends up being x is equal to 1/2 u plus v, and y is equal to 1/2 v minus u. So now if we take the Jacobian, take the derivative with respect to u is 1/2, respect to v, respect to u, and then finally respect to v. And this gives us 1/4 minus minus makes plus 1/4, what gives us now a positive 1/2. There we go. Okay. So now if we take the integral, now we're just respect to u. So v is a constant, so this is like a 5. So we have to use, I'll use w this time. So derivative of the top, so it'll be uv, so dw is going to be just v du. It says v is a constant, we have to divide it over. So when we divide it, those v ends up canceling. So we just get the integral of e to the u, which is just itself. Right? That's nice about e to some powers. So this ends up being e to the, or just put the 1/2 on the outside, e evaluated to the uv, evaluate at 0 and 2. So I'm plugging in 2 in for u, so this ends up being e to the 2v minus 1, because e to the 0 is just 1, times 1/2. Okay. So one more integration. So finally, again, I'll just bring this to the outside. Integral from 0 to 3 of e to the 2v minus 1 dv. Again, another quick little u-substitution, so let w equal 2v, then dw is equal to just 2, dv, divide by 2, so this ends up being 1/2 times 1/2, which is 1/4, evaluated at e to the 2v minus v, because the integral of 1 is just v itself, at 0 and 3. Okay, so do it one more time. Plug in 3, we get 6. Plug in 3, we get 3. Minus. Plug in 0, we get 1. Plug in 0, we get 0. So it gives us that. So we get e to the 6 minus 4 all over 4. That's our answer.